The Newton is the SI unit of force. 1 Newton is defined as the magnitude of push required to accelerate 1 kilogram at a rate of 1 meter per second squared. Now here near Earth's surface, we know that objects fall with a higher acceleration than 1 meter per second squared. It's actually 9.8 meters per second squared. And what this means is that more newtons are being exerted on each kilogram here near Earth's surface. So how many newtons does gravity actually exert on 1 kilogram? Well, in order to get the acceleration to be 9.8 times higher than 1 meter per second squared, the force of gravity has to be 9.8 newtons. How many newtons, though, would gravity exert on a system of 2 kilograms? Well, if we treat each mass as its own system, then by the symmetry of the situation, what we should find is that Earth will pull on both of them with 9.8 newtons equally. However, when we combine them into one system and treat the object as a 2 kilogram object instead of 2 separate 1 kilogram objects, now Earth pulls down with 19.6 newtons on the system combined. What this shows is that as the mass of a system increases, the force of gravity acting on that system increases as well. So I'm going to fill out this table, and what it shows is several different size masses, and we want to actually calculate what the weight or force of gravity acting on them would be here near Earth's surface. Now when it comes to the acceleration, we've observed that all objects fall with the same acceleration, 9.8 meters per second squared, no matter how much mass the object has. So all of these are going to have 9.8 as their acceleration. All right, now we want to find out how much force would act on each of these objects. Well, we already said that a 1 kilogram object will feel a force of 9.8 newtons. And I said a mass of 2 kilograms would feel a force of 19.6 newtons. That means that a 4 kilogram object would feel 39.2 newtons as a system, and half a kilogram would only have 4.9 newtons. And a quarter of a kilogram, 2.45 newtons. So what is the formula that governs this? Well, it is the formula for weight of an object. I said before that the force of gravity was going to be proportional to the mass that's in an object. And what this means is that there will be some constant times m in the formula. The constant is the gravitational field strength, which is G. And so this is a formula for weight of an object. Here are some details. Both W and FG represent the weight of an object, and it'll be the product of the object's mass times the acceleration due to gravity. If we're on the moon or some other planet where the acceleration due to gravity is different, then we would use that specific value for that moon or planet. Here on Earth's surface, it's always 9.8. It's important to note that objects have weight even if they're not currently accelerating. Weight of an object is a vector, so it has a direction in space. The direction of weight is the same as the direction of the acceleration due to gravity, which is always down toward Earth's center. The gravitational field represents the idea that no matter where mass is located around Earth, it will accelerate toward Earth. A with a subscript g is the acceleration due to gravity, and it's often called the gravitational field. The gravitational field around Earth always points toward Earth's center of mass. An object's weight on Earth always points toward Earth's center of mass because gravity is an attractive force. R hat is a unit vector which points away from a point or a sphere such as the Earth. Now I want to give an example of that. Let's say that that represents the Earth. And this is the center of Earth. Now we want to pick some point around Earth at which we want to evaluate the gravitational field. So let's pick some random point that's just off Earth's surface. Now the acceleration due to gravity can be written as 9.8 newtons per kilogram in the negative r hat direction. Now first of all, what do the units newtons per kilogram mean? It means that depending on how many kilograms are present in the field, this is how many newtons Earth will pull on that system of mass. So if we have 1 kilogram in the field, Earth is going to pull with 9.8 newtons. If we have 2 kilograms in the field, Earth will pull with 19.6 newtons. And the size of the pull will depend on how much mass is present in the field. It is very useful units to use for the acceleration due to gravity. And it can be shown that meters per second squared is actually equivalent to newtons per kilogram. All right, now, what about r hat? What does that mean? So r hat actually points from the center of a mass such as Earth radially outward, and it'll be directed toward the point where we're evaluating the field. So this is r hat. But the gravitational field actually points in the negative r hat direction, which should make sense because gravity is an attractive force. So this is negative r hat. All it means is that no matter where we're located around the sphere, the direction of gravity is always going to be inward towards center. That's negative r hat.